present this very simple-minded use of restricted Boltzmann machine as sorry, it's working, I hope, to see the usage of RBMs as variational and guiding wave function for quantum Monte Carlo, and we apply that to a specific 2D bosonic model. So this is ongoing work with my PhD student Hugo Thévenot, and this is a Netgate session. So I shall say that there's going to be a lot of Netgate inside. So you know everything about RBMs by now. You know they're a very good usage as a variational ansatz for a ground state of many body systems, especially in 1D, in the work of Giuseppe and Matthias Treuer. Using more layers, you can actually find that you have a nice competitive method, a variation method for studying strongly correlated systems in 2 dimensions, in particular frustrated magnets or in general systems with competing interaction. But besides the conceptual advances, I would like to say that, of course, the technical computational advances made in the machine learning community can also be very useful. And Giuseppe just emphasized that both aspects, physics and the technical aspects, are implemented in Netgate. So we will use Netgate for studying a specific 2D bosonic model, which I'm describing right now. So this is a model of hardcore bosons on the square lattice geometry. And the key players are these ring exchange moves, where you can see that 2 bosons are moving together in a ring exchange fashion. This is a K1, K2 model, which has been introduced by Motronish and Kobokes, which features a competition between 2 ring exchanges. The first one with a coupling constant K1 here on a single plaquette of the square lattice, and with a coupling constant K2 on the ring exchange on a 2x1 or 1x2 plaquette. So 3 remarks are in order. The first one is that there is no single boson kinetic term. So there's no superfield instability, which is possible in that model in the ground state. Second important point is that this dynamics actually implies some several conservation laws. In particular, the number of bosons per row and line, per row and column, sorry, are conserved. You can really check that very easily. And this talk, I will consider this specific feeling. Finally, the coupling constant K1 and K2 will be chosen as a positive, which means that this model has no sign problem. But the point is that it's not easy actually to write an efficient path integral quantum Monte Carlo code or algorithm for this model, which is mostly due because there is no single boson orbit. So that's for the technical aspect. Now, what about the physics? This model is very interesting, as emphasized by Motronish and friends, because it's supposed to host at large K2 a new phase of matter, which is this Bose liquid, which is a phase which has no long-range order. It's a liquid, but at the same time, it has gapless excitation along lines in the momentum space, a bit like a Fermi surface for bosons. So that's very unusual. At a smaller K2, we have more conventional crystalline phase. So this phase diagram estimate has been obtained by a really nice work by Motronish, which physically inspired Jastrow a parton wave function, as a matter of fact, with VMC and actually also with nice QMC on 12x12 lattices. So now let's see what RBM can do in front of this 2D complex model. So what we find is that the simple RBM actually give excellent variational energies. Of course, we want to use as much as possible symmetries in the RBM. Symmetry is the problem, so we can use translation, rotation and reflection of the square lattice, C4V, particular symmetry, and also we want to use the fact that the wave function is real and positive. And let me emphasize that all our calculations are done within Netgate, where all these symmetries can be handled very easily. Something which is also very nice in Netgate is that you can choose your custom or Hamiltonian sampler. And this is very important for this problem because we need to conserve the number of bosons per row and column in the sampling. Otherwise, the wave function has 0 coefficient. So here are the results of the RBM as a variational wave function on a 6x6 and 12x12 for various symmetry implementation of RBM. The one with less symmetries is here. Then we had the translation, and then translation, rotation, and reflection. And what we see is that we converge very nicely to the ground state within error bars. The ground state exact result is a pink line on the 6x6, and that's also here possible on the 12x12 for different values of parameter. And we see that we really have an excellent accuracy compared to the exact results. We also outperforms previous VMC calculation by Motrunish. To be honest, there were less parameters, but still at very small values of alpha, we can really get a competitive energy. And even on the large lattices, we actually see that we can converge the RBM to be a relative error to be like 3 to the 10 minus 3 to the correct result. So the correct results, as you can guess, is obtained using QMC. I shall emphasize a final point. Of course, it's always better to use symmetry, as you can see here. We really decrease the energy, but sometimes we found that using too much symmetry slowed down the simulation, in particular the C4V. For instance, we were not able to run very large alpha using all possible symmetries in such a way that sometimes it's actually, we found it's better for this model to use only translation symmetry. Okay, so this is the first part. So we can use RBM. They give excellent variational energy, but we can do better. Indeed, this model has no sign problem. So what we wanted to do is combine the expressive power of RBM to the sampling power of QMC with no error besides statistical error. And we do that in a so-called habitation QMC framework in its method, which has been proposed by Baroni and Moroni, and you can learn about much more in this book, which is nicely written. It's a very basic idea. So basically, you just project with a large power the Hamiltonian on top of some trial wave function, which we take to be the RBM here. And you insert several resolution of identities, some over all possible configuration in such a way that the configuration space takes the form of a reptile with M or M plus 1 configurations like that. And you move in this configuration space by proposing a move according to the Hamiltonian dynamics. So let's say I want to move the reptile in that direction, changing the last configuration to be a new one, C prime. Let's imagine I accept this move. What I need to do now is to delete the vertebra at the tail of the reptile in such a way that now I have a new reptile which has moved in the right direction. If M is large enough, you should converge to the ground state. And you converge better if you use a correct guiding wave function. So as the move from Cm to C prime was done according to the Hamiltonian dynamics, proportional to matrix element, times the ratio of the guiding wave function, which we again take to be the RBM. So of course, there's some additional cost to do that. We estimate it to be of the order of alpha n, where R is the total number of lattice sites, but it's really worth it. In the end, if M is large enough, the power is large enough, you can measure the energy at the head or tail of the reptile, and you can measure a diagonal observable in the ground state, really in the middle of the reptile. Due to this cost, we found that it's best to work with relatively small value of alpha as a guiding wave function. What is really nice about NetEd, again, is that you really have access very easily to this ratio wave function, and we implemented actually this full reptation guided by RBM or by any wave function actually as a new ground state solver in NetEd. So here are the results. It's really beneficial to use a guiding wave function, as everybody in QMC knows. For instance, on the 6x6 or on 12x12, if you actually, you can check the difference with no guiding wave function, which are the black curves, and with the RBM at alpha equal 1, very small value of alpha. Already at projection index 12 or maybe 20, we are in the ground state, the exact ground state for the 6x6. And that takes much more time with no guiding wave function. And it's even more clear here, perhaps, on the 12x12, where even without a guiding wave function, we are not even sure that we actually converge at this large projection index to the ground. Okay, so far for technical aspects. Let's see what physics we can learn from this quantum Monte Carlo. So I will evacuate very rapidly the physics at low K2 because we know what it is. It's a charge density wave, for instance, at K2 equals 0. This can be proved by looking at the structure factor at pi pi. It's like Néel order, if you wish. And we can see where it vanishes. Identically, we can look at the Bieder cumulant of the order parameter associated to this phase, and we see a crossing point around 0.4. This was actually known from the previous work by Motrunish. We can do the same phase for the next crystalline phase. This time the structure factor, it's this plaquette structure factor, which is a bit more complicated. It involves these operators. And, the results are in the same idea. It's a bit more difficult to actually pinpoint the place where the plaquette structure factor vanishes. But if you look at the Binder cumulant associated with that, it seems to be crossing around between 3 and 4, probably closer to 3. Okay, so these two phases were simpler to detect because we have an order parameter. Now, what about the Bose liquid? It's more complicated. Indeed, we have no long-range order and no broken symmetry. So what we decided to do is to look at very naively at the structure factor in the large K2 equals 7 limit. And I hope you can see this movie where we should identify two things. First, there is no obvious diverging Bragg peak. We check with fine size effect that there is no peak in the density structure factor. And also, maybe let me play again the movie. You see these cross lines where the structure factor is actually 0. This is of course very natural in this model. But what's perhaps more important is the fact that we have this V shape here, which this singular behavior, which has been identified as a signature of the excitonic Bose liquid in the field theory by Motronish once again. Actually, the field theory can do more and predicts that the EBL phase should be stable if this slope here, close to the gapless line, is large enough. So the slope is something like that. It has to be larger than some threshold value. We computed that slope as at the smallest possible wave vector in the x direction as a function of ky. And we find that at large K2, the slope is over the threshold value for most of the ky values, so which we take as an indication that the EBL phase is indeed stable. But at K2 equals 4, where we are supposed to leave the plaquette order, it's less clear that the phase is stable, at least with no data. So this is what we did so far using quantum Monte Carlo, biased by the RBM wave function. Now we would like to do a bit more, but sometimes in quantum Monte Carlo, it's difficult to actually compute some complicated correlation function, or in particular the entanglement entropy. This is possible, but this is kind of hard. It's much simpler if you have the wave function. And this is what we did recently. We wanted to use the best possible RBMs, which we saw were very good, up to 3 to the 10 minus 3 precision in energy, to actually compute complicated things like the, for instance, the Rényi entanglement entropy. So we heard in the last talk that if we have the wave function, we can compute using this nice trick by Hastings and Melko, which is called the swap trick. So let me recap it for you. Let's say I want to compute the Rényi entanglement entropy of order 2 within this choice of entanglement block. So what I need to do is to sample my RBM and create two copies, two different configurations, and I just need to swap the bottom part, the A part, the entanglement part block between the two configurations in such a way that in the end, the entanglement entropy is just given by the ratio of this wave function, like that. And that's really just a couple of lines in Netcase. That's really nice, so once again. So here are the final results. So let me emphasize 2 points in this block geometry where we take the block entanglement to be one line, or LA line in general. What we find is that we need to go to very large alpha actually to converge to the, even on a 6 by 6 to converge to the exact value for the entanglement entropy. If you take just alpha equal to 1, you don't get the correct value. On the physics side, we find that if the entanglement block is just one line, the entanglement at low K2 is larger, sorry, than for two lines, which is against the area law. So we attribute this parity effect to the demineralized, to the crystalline phase. So we can do the same things on a different geometry. And we also find, which is this square LA by LA, this very strong parity effect. In particular, for instance, the LA equal 3 by 3 block has a much larger entropy than the 4 by 4 or even the 6 by 6. So we are actually fighting with noise effects, but we hope that we will be able, and that's possible because we can really sample the RBM nicely, we'll be able to overcome disparity effect in the both liquid phase. And so this is pretty much work in progress. So okay, I think my time is over. I would just like to emphasize that this constraint model in 2D and 3D are have very interesting physics, and that can be probed with a type of neural network techniques plus or minus habitation Monte Carlo. Okay, so let me stop here. Thank you very much.